Thank you everyone for being here. So I'm presenting today some of my work at Columbia University. This is about enhancing carbon intake for magnesium oxide-based structures. Currently, I'm at Purdue University working with Dr. Kendra Irk and Dr. Oleg. I just want to make sure that this is the work I did with Balashpat Katia and Shiho Kawashima. So I think one of the reasons we're all here is because we know concrete is one of the most used materials on Earth after water, and because of it, it produces a lot of carbon dioxide. And if we actually go dive deeper into where this carbon footprint of concrete comes from, we can see that almost the majority of it comes just from cement production. And of the cement production part, the main part comes from simply the decomposition of the carbonate phases inside cement. And specifically, if you look at calcium carbonate, which is just what we were talking about, we would see that by itself, it's responsible for 33% of the CO2 emissions of concrete worldwide. And so if we are trying to reach the goal of reaching carbon neutrality of concrete, we would have to at least put back all the carbon dioxide that we have produced by making our concrete, putting it back in. However, the best that we could do is put it back in and reach carbon neutrality. So one of the questions that I wanted to answer is, can we go a step further? Can we start to talk about carbon negative concrete? And for that, we have to sort of forego the calcium base and look into another mineral. And that is where magnesia comes from. Now, magnesia or magnesium oxide is not novel. It's actually been used since 150 years at least. It's part of almost every cement batch. Typically, it's used at 1%, and in some large structures, we use it at 5%. However, we don't use it as the main binder, simply because it's weak. This is how it looks like after you cast it for 1 day. This is technically hardened, and it can barely sustain its own weight. And this is typically why it's not used as the main binder. However, magnesium have a trick. Once it hydrates, it can actually carbonate. And when it's carbonated, we can see that it can gain a lot of physical strength. Now, the physical strength it gains when it's carbonated, when it's casted, is still not high enough to use it as a construction material. But that's where the idea of using 3D printing comes from. So if we look at atmospheric carbonation of a casted specimen, we typically try and place it in a low carbonation, low pressure, high carbon content chamber, and that would sort of start to carbonate the sample. But because carbonation is an outside-in process, which means carbon have to go from the outside of the specimen and penetrate through, we would not be able to fully carbonate it. So what we would end up with is a carbonated shell with an uncarbonated weak core, and that's why we see the slow compressive strength. So the benefit that 3D printing can give us is create these delicate internal structures that allow us to create carbon delivery channels, increasing carbon penetration, and therefore maximizing the compressive strength. So that's the research that I did at Columbia. So to be able to make this material printable, that's too weak to sustain its own weight, even when it's hardened, I used a mixture of nanoclays and viscosity modifying admixtures. Now, the nanoclays that I use are made of purified magnesium aluminosilicate. This is sort of how they would look like. They're around 30 nanometer diameters and at 1.5 microns in length. And they typically come in very agglomerated states that we have to disperse, but they're rather very easy to disperse and they're very friendly to use on site. And then the second part is methylcellulose, which is just a viscosity modifying admixture. And I'll talk very quickly about why I use this combination. Now, to characterize the rheology, I just relied on a typical vein and cup geometry. And the protocol that I use is rather very simple. The one note that I have is I typically use a very long pre-shear. Typically with 3D printed concrete, we reach very high structuration. Typically in literature, we typically used to use rheology for self-compacting concrete. And that meant that the pre-shear time required was 1 to 2 minutes. But when we are now talking about thousands of pascals of static yield stress, that requires significantly high pre-shear rates. And that's why I apply a very long one for 20 minutes. And then I can measure my static yield stress, which is simply the peak of my low strain rate applied after some rest time. So rheologically, I can transform my magnesium oxide paste from material that cannot sustain its own weight when it's hardened to material that is highly printable. However, with the use of nanoclays, just because they are of the nanoscale, the increase in static yield stress is accompanied with a lot of increase in stiffness because it can only operate within this very small strain range. And that's where you can see here in the print that I made, you can see that the filament looks very dry. So this is a freshly printed specimen. However, the filament is very stiff that I'm extruding it as a solid rather than a liquid. And this is where we see that we're going from roughly 2 to 10 pascals into almost 800 pascal of static yield stress. So it's thousands of percent of increase in static yield stress. That's why it results in this phenomenon. So the second part is why I add the viscosity modifying admixture. So rheologically, if you look at the static yield stress, there's very little gains, and in some cases you would see detriment to adding something like a viscosity modifying admixture. However, what we would see on the realm of the 3D printing performance is instead of printing with a solid material, so when it's being extruded, I'm not extruding as a solid region, I actually can deposit it in a liquid form and then let it act as a solid afterwards. And that drops the stiffness of the material as it's being extruded, meaning I end up with better filaments. So when I was able to 3D print the material, then I created an experimental program looking at 3 different infill patterns. This is a video of how the second infill pattern is being printed. You can see here that 2 open internally structured infill patterns of small specimens, and then a third one which is closed, and this is meant to mimic a cast specimen, just to be able to isolate what are the changes happening because this material is being 3D printed. So very quickly, we can look at the compressive strength results. So at 3 days of carbonation, so these are specimens that were cast 3D printed, left for 1 day, then placed in a carbon chamber to carbonate. At 3 days, we can see that all 3D printed specimens have significantly higher compressive strength. We're seeing increases from the cast specimen, and those are the carbonated ones, between 400 to 500% increase. And at 28 days strength, we see that we are still gaining significant amount of strength. Now, the water to binder ratio here is much higher than what you typically would expect with cement. And that's sort of what makes it rheologically more difficult to 3D print. But then we can see here that at 0.9 or 1.1 water to binder ratio, we are gaining significant amount of strength. And in some cases, we can gain strength up to 50 megapascal, and that's quite sufficient to use this as a structural material to be able to build with it. Now, what was interesting to me is that typically what we would expect with cement, as we increase the water to binder ratio, we would end up losing strength. And what I was finding here, which was strange to me, opposite to the early age, that my mixes with the higher water to binder ratio were the ones with the higher strength. And the second part that was interesting is the samples with closed infill, so no internally hollow structures, were also keeping a similar strength of the open internal structure. And I expected them to be something similar to my cast specimens. And it was a bit of a head scratcher to understand why this was happening until we finally decided to look at the mass changes of these specimens, not only when they are carbonated, but even before that. So between 0 to 1 days, because my samples are not hardened, I did not move them, I waited for hardening. So within that first 1 day, my casted specimens are sitting inside their protective molds, so they're only exposed from the top for air evaporation. Whereas my 3D printed specimens have a much higher water evaporation. Now, with concrete, this is a big problem because it causes a lot of shrinkage and that weakens the material. But with magnesium oxide, this high amount of water evaporation is actually increasing porosity. And with this increase in porosity comes an increase in carbon penetration, and that then continues to increase my compressive strength. So what you see here with this higher increase in water evaporation or the greater mass loss with 3D printed specimens, even when it's a closed infill, just this higher exposure and those delicacy between the interlayer and interfilamentous paths that we typically see as flaws, those are actually aiding in carbon penetration. So just by the fact that magnesium oxide is now 3D printed we are now observing significant amount of carbon intake. Now, the benefit to this mechanically is also when magnesium oxide, after it's hydrated and carbonated, it actually expands and increases in size. So all these pores are getting filled up with magnesium carbonate. So that's why we can see a very good, so in fact, to be able to use the system, we'd rather increase its water evaporation, and that's where the mixture with the higher water to binder ratio, as you can see here with the 3D printed one, the one with the higher water, which means higher evaporation, meant higher carbon intake and meant higher compressive strength. So with this, I can conclude just the main summaries of my talk, which first of all is nanoclays were successful in increasing the structuration rate and to enable the 3D printing of this material. This is very tough material to print. We can't rely on accelerated hardening like we would in typical Portland cement, simply because it's hardened straight when it's hydrated is still too weak. So in this case, the static yield stress is the one thing that's carrying all the 3D printing performance. And then when we can 3D print it, we can reach compressive strengths between 40 to 60 megapascal, which is sufficient to use it as a structural material. And then, like I said, we are using the high water evaporation, and we are working on more research on how we can maximize this further and further. And lastly, this is one way we would be able to go back into a carbon negative concrete, and rather by finding ways to harvest magnesium oxide in carbon neutral ways, we now have a material that consumes carbon dioxide in order to gain compressive strength. So with that, I would like to thank you. If you're interested in this, our paper is already published. Hopefully this would work. You can scan the code to get the paper, and I'll be happy to talk about this.